It's funny. Have you ever noticed how some patterns just seem to pop up everywhere you look? I mean, from the heights of people in a crowd to tiny errors on a scientific measurement, it feels like nature has a favorite blueprint it just loves to use. Well, today, we are going to crack the code on that exact blueprint. Let's dive in.
But first, let me throw a little puzzle your way. Imagine you ace your history test with a 70, and your friend gets an 80 on a super hard math exam. So who did better? The answer is, you have no idea, right? They're totally different tests, probably with different averages, different difficulty. It's like comparing apples and oranges. Keep that problem in mind because we're about to solve it.
And the solution starts with spotting a pattern, a universal pattern that, believe it or not, secretly organizes a ton of the data in our world.
And this right here, this is the pattern. It's the famous bell curve. And I promise you, once you really see it, you'll start spotting it everywhere. This shape is no accident. It's a fundamental pattern in statistics that brings a beautiful, predictable order to things that might seem totally random at first glance.
Now, this famous bell curve has a proper name, and getting to know it is the key to unlocking all of its power.
Officially, it's called the normal distribution. You might also hear it called a Gaussian distribution. Now, the two words you really want to lock in on here are symmetric and bell-shaped. Symmetric just means it's a perfect mirror image of itself, perfectly balanced around the middle. And bell-shaped, well, you can see that. It just means most of the values are clustered in the center, and they get less and less common as you move away.
And here's what's so wild. Every single normal distribution in the universe, no matter what it's describing, is built from just two ingredients. First, you've got the mean, that little Greek letter mu, which is just the average. It's the absolute center, the peak of the bell. And second, you have the standard deviation, or sigma. That's just a fancy term for how spread out or squished together the data is. Is it a wide, flat bell or a tall, skinny one? The standard deviation tells you that.
Okay, enough with the theory, let's make this real. We're going to use a simple example. Let's just pretend we have some data where the average, the mean, is 50, and the standard spread, our standard deviation, is 10.
So there it is, the peak of our curve, the most common value. The center of its universe is sitting right there at 50.
Now let's put that standard deviation to work. If we take one standard step above the average, we just add our standard deviation of 10 to our mean of 50, and that lands us at a value of 60.
And you can probably guess what happens if we take one standard step below the mean. We subtract 10 from 50, which puts us at 40. So these three numbers, 40, 50, and 60, they kind of form the basic skeleton of this particular bell curve.
But this is actually where the problem starts. See, if every set of data has its own unique center and its own unique spread, how on earth can we compare them? We need some kind of universal standard. And here's the crucial idea. In our example, a score of 60 is pretty good. It's one full step above the average. But imagine a different set of data where the average is 70. Suddenly, that same score of 60 is actually below average. So the number 60 by itself is totally meaningless without context. So, what's the fix? Well, statisticians came up with a brilliant idea, a golden ruler, a single universal reference point that we can compare everything to. It's called the standard normal distribution, and its rules are super simple. The mean is always 0, and the standard deviation is always 1. It's the one blueprint to rule them. Okay, that's great. We have a golden ruler. But how do we get our data, with its own weird mean and spread, onto this universal scale? We need a translator.
So, what's the magic trick? What's the key that lets us translate a score like our 60 into this universal language?
It's called a z-score. And honestly, if you take one thing away from all of this, let it be this. A z-score is a beautiful thing because it just rephrases the question. It doesn't care about the original number. All it tells you is, how many standard deviations is this specific point away from its own average? That's it. And the process is so wonderfully simple. Let's take our score of 60 again. First, how far is it from the mean of 50? Well, that's easy. It's 10 points away. Then, you just ask, okay, how many of our standard deviation steps is that? Since our step size, our standard deviation, is also 10, the answer is exactly 1. So the z-score for 60 is positive 1. Simple as that.
So we've covered the how, but now for the most important part, the why. Why on earth do we go through all this trouble of translating things? Well, this is where the magic happens.
Because once everything is on this universal scale, we can suddenly do amazing things. We can finally compare those test scores. We just turn your 70 and your friend's 80 into z-scores. And whoever has the higher z-score actually did better relative to their own exam. We can also see at a glance if a data point is totally normal or incredibly rare. This whole process provides a common ground for all data analysis, and it's the foundation for way more advanced statistics.
So when you boil it all down, this whole process, standardization, it's not really just a math trick, it's an act of translation. It takes data from thousands of different, confusing dialects and converts it all into one single universal language that anyone, anywhere can understand. It's a universal ruler. And that leaves you with the question, what other things in your life seem completely incomparable, but maybe, just maybe, could be understood if you only had the right rule?